All right, next example I wanted to look at is one where the object doesn't quite make it all the way around the circular path. In other words, it starts out at the bottom with some initial velocity, but that initial velocity is not enough for the ball to make it all the way up over the top and still maintain tension and the strength. Okay, and so we saw in our previous example that to just make it up over the top, the velocity at the bottom has to be the square root of 5rg without friction. And so what I'm going to do then is, because I wanted to make it most of the way, but not quite all the way over the top, I'm going to make it the square root of 4rg at the bottom. Okay, and so this is what I'm going to set up as my initial velocity. So let's say that r equals 10 meters and g equals 10 meters per second squared. Then v naught would equal 2 times the square root of 10 times 10, or that would be 2 times 10 is 20 meters per second. I'm going to leave things in terms of r and g for the moment, but that would be the actual value for this problem if we set r equal to 10 meters. So what I'm asking then for in this problem, since it won't make it all the way up over the top, is at what point will the cord go slack? In other words, at what point does the ball leave the circular arc path and start to follow a parabolic path? Now, if this were a car that's going around a loop-de-loop track, that'd be the point at which the car would leave the road and would be in big trouble. So for this problem, we have a little more going on than we had in that previous example. Let's take a look at the mass at the point where the tension goes to 0. So we're going to have a tension force here. If this angle is theta, then this angle is also theta, because opposite interior angles are equal. So I'm going to write it in terms of this angle as measured from the vertical. And so that means then that the component of the weight force that is acting to enhance the centripetal force is going to be mg cosine theta. And so our centripetal force equation, which we're definitely going to need here, will look like the sum of the inward forces equals mv squared over r. And so that'll be t plus r, t plus mg cosine theta. Okay, and so if we look then for the minimum velocity, that'll happen when t equals 0. And so this could also be a normal force if this were a car going around a circular track and not quite making it to the top of the path. So under those conditions, then the minimum velocity would be defined by mv squared over r equals mg cosine theta. That would give us v is equal to root of rg cosine theta. So that's our condition then on the velocity of the mass at the point where the tension goes to 0, which is basically what we're looking for here. It's the maximum height of the ball before the cord goes slack. Now the height I can write in terms of h here, and we see from the picture that in terms of r, h is going to be r plus r cosine theta. And so I'm going to replace h by r plus r cosine theta in this figure. I can call this height here y initial equals 0. So this is going to be my y final at the point where the ball leaves the circular arc path. So So now we have enough information to write the energy equation. Let's do that. 1/2 mv naught squared plus mg y naught equals 1/2 mv final squared plus mg y final. No need to add in the work done by friction, absolute value of the work done by friction, or the spring terms, since there's no springs in the problem and we're assuming, again, that there's no friction. Okay, so the y initial is 0. Y final, though, is not 0 because we're still need to have the tension just go to 0 at this point. And so that means that we have this balance between the inward force that is acting, mg cosine theta, and mv squared over r. So we can rewrite this then on the left as 1/2 m times 4rg, because v naught at the bottom is 2 times the square root of rg. 2 squared is 4 times the square root of rg squared is just rg. That's 1/2 mv naught squared. 1/2 mv final. The final we've got over there, that's the square root of rg cosine theta. Then that's squared, which gets rid of the square root sign, plus mgh, which is going to be r plus r cosine theta. Okay, so on the left, we can simplify this a little bit all the way through. And this will give us 2 mrg equals 1/2 mrg cosine theta plus mrg plus mrg cosine theta. And so the rest of this then is just going to be a solution for the cosine of theta, because the mgrs are going to cancel all the way through. They're common terms. Common multipliers in every term. So this gives us then 2 equals 1/2 cosine theta plus 1 plus cosine theta. Okay, so the 2 and the 1, when we subtract 1 from both sides of the equation, we just get 1, and that'll equal 3/2 cosine theta, giving us then, for our solution, cosine of theta is equal to 2/3. Okay, so as was the case in a previous example, we don't really need to know what theta is here, because our answer for the height is written in terms of cosine of theta. So all we really need to do then is say that h is equal to r plus r times 2/3, which is r plus r cosine theta. That gives us 1 2/3 r, or 16.66 meters if the r value is 10. Okay, and so that is the height at the point where the cord goes slack. Right? And so this is a little more challenging than some of the other problems in that not all of the gravity force is pointing toward the center, just the cosine theta component of it. And in contrast, when we reach the peak of the path in a previous example, and we got the square root of 5rg for the initial velocity, then all of mg was pointed in the down direction. So here we just had to look at that part of mg, which is pointed toward the center of spin, and then set that equal to our centripetal force, which we should be getting used to now is mv squared over r. Okay, so that is another example then of a good combination problem that is quite possibly could be seen on another quiz. Take a look at a couple other examples. Let's say we had a problem where we have a mass that moves along with some initial velocity, v naught, and then that mass encounters a spring with a natural unstretched length that I'll define by this position, x naught, and then the mass compresses the spring by a certain maximum amount. Okay, so that in the final configuration, this is x equals 0. The mass is here and has compressed the spring by an amount that's equal to x. We'll call it x naught. And while this is happening, let's assume that there's friction on the surface. Okay, and so on this surface, let's say that we have a coefficient of kinetic friction that's equal to 0.5. Okay, so for this problem, if v naught, let's say, is equal to 10 meters per second, and the spring constant is equal to 1,000 Newton per meter, let's find the maximum compression distance. X naught of the spring with friction on the surface. And so what I'm going to do here is set this problem up, because this is one that I'd like you to finish on your own as an exercise that might help you with future quizzes. Okay. And that what we have here is an energy equation. We can say that there's really only one external force in this problem. And that external force is the force of friction. So we can write this as energy before 1/2 mv naught squared plus mg y naught plus 1/2 k x naught squared equals, it's final, 1/2 mv final squared plus mg y final plus 1/2 k x final squared plus the absolute value of the work done by friction. Remember, this is the way that we wrote it before. Or equivalently, we could have put the work done by friction on this side, but it would be negative, which means that to make it positive, we'd move it over to that side. But either way, this would be the equation that we could use to solve for x final. Okay, so our initial velocity then is given. We do need the mass, because the mass here is not a common factor in every term. So let's set the mass equal to 2 kilograms. Okay. And x naught and x final don't come into play here, because we can set them both equal to 0 since the mass is moving along a horizontal level surface. Okay, and so what we're left with then is, and we have the k value. So what we're left with then is the no initial spring energy, but we do have final spring energy. At the end, the spring has been compressed by a certain amount, but it's not compressed initially. So this term is also 0. So all the energy at the beginning is just the kinetic energy. And there's no final kinetic energy because it comes to rest at the maximum compression distance, which here I'm calling x final rather than x initial because this is the final point, the way that I'm writing the energy equation. Okay, and so what we're left with then is just 1/2 k x final squared plus the work done by friction. So that'll be the coefficient of kinetic friction times the normal force. Normal force is just mg in this case, times the distance, which is x final. So that's the distance that the mass has slid. Okay, and so now we can plug in numbers for all of these values, assuming that we know the coefficient of kinetic friction is 0.5. So this gives us 1/2 times 2 kilograms times v naught squared, that's 10 meters per second squared, equals 1/2 times k, which is 1,000 Newton per meter, times x final squared, plus mu 0.5 times mg, 2 kilograms times 10 meters per second squared, times x final. Okay, so working this down a little farther, we get 100 equals, here we've got 500 x final squared plus, and then 0.5 times 2 is just 1, so that's going to be plus 10 times x final. Okay, so what we see that we've got here for the compressed spring distance in the final configuration is a quadratic equation. So you can solve this for x final. So I'm going to ask you to do that as an exercise and then compare that result to what we would have without friction. Without friction, we would expect a slightly larger value for x final. So that's a way for you to double check your result if you just solve this equation for x final in the absence of friction.